Hey everyone, now that we've reviewed atoms and electrons and types of bonds and polarities, let's start putting our atoms together into molecules. And we're going to look at two different ways to account for the electrons and the bonds of molecules. Okay, the first way is really a bookkeeping method. It makes sure that we know exactly where the electrons are and how they're being used, and then we're going to move on to some other ways to make our molecular drawings more straightforward and faster and simpler. We're going to start to simplify them so we can do them much more efficiently. All right, so we're going to start out with what we call Lewis structures. We're going to then look at Kekule structures, and then we're going to go on to what are called skeletal structures. So the skeletal structures are really the ones that we're going to use predominantly during this class. So the first thing we're going to look at is these Lewis structures, and I know you guys have some practice and some experience doing these in Chem, but we're going to review these because these are really the structures that allow us to look at the real nitty-gritty of counting up electrons and things like that. So we're going to look at 4 different steps when we do Lewis structures. Okay, so the first thing we need to do is we need to know how many electrons we're working with. All right, so we're going to first determine the number of valence electrons. And remember that the number of electrons, valence electrons, can equal the number of protons for each of the atoms, except for when we have a charge in the molecule or on the atom, right? So if we have a negative charge, then we're going to add 1 electron because we know we have 1 more electron than we have protons. And if we have a plus charge, we're going to subtract 1 electron. So first thing, add up the valence electrons. Next thing we're going to do is we're going to use electron pairs to form bonds, and we're going to use dots for the electrons. Typically the H's are always going to be on the periphery of the molecule, right? Because H's can only have a single bond. We're going to complete the octets of the atoms after we've made the bonds by either using pairs of electrons for lone pairs or non-bonding pairs, or by making multiple bonds like double bonds or triple bonds. And the last thing that we'll do is to assign any formal charges. So if our molecule has a minus or a plus, we're going to have to figure out what atom that belongs on. All right, so let's start just by a very simple example right here. We'll just do the Lewis structure of water. All right, so the first thing we want to do, number 1, we want to determine the valence number of electrons, or the number of valence electrons. So to do this, remember we have to know this upper part of the periodic table. So for oxygen, how many valence electrons does oxygen have? All right, so if we look at the periodic table, we'll do that in the next slide, we'll see that oxygen has an atomic number of 8. Right? We want to remove the 2 electrons in the first row, and so oxygen has 6 valence electrons. And then we have 2 hydrogens. Each one of those brings in 1 electron. So we have 2 electrons. So we know that our Lewis structure for water needs to have 8 electrons in it. All right? So we're going to start with oxygen in the middle. We know that hydrogen has to be around the outside. And we can just draw our 6 electrons around it. Right? It makes sense. If we just start with 4, we have 2 more. So let's put those in pairs. Right? And we see that we have 2 lone electrons. Right? These are the ones that are going to pair up with an electron from hydrogen, like this. And so we get our water molecule. We notice now that each of the hydrogens has 2 electrons, so that's a full shell. The oxygen is able to count all of these electrons, so it has its octet. All right? So the valence electrons we're going to be able to know just from the periodic table, and remember that especially this row right here, well, hydrogen, are going to be important to know. We want to know that carbon has 4 valence, nitrogen has 5, oxygen has 6, and then as we go down the halogens, all of the halogens have 7 valence electrons. So these are going to be the most important to know. All right, so let's look at some more examples here. Okay, let's start with C2H6. All right, so let's calculate our number of our valence electrons. Okay, so we have 2 carbons. Remember, how many valence for each carbon? Each carbon has 4, right? That's the number of bonds it's going to make. So we have 2 carbons, gives us 8 valence electrons. We have 6 hydrogens. Each one of those has 1 electron, so we have 6. So we have to account for 14 valence electrons. So our final structure should have all 14. All right, so let's just start out by drawing our 2 carbons. And each of those carbons is going to have 4 electrons around it. All right, if we have 2 carbons and the hydrogens are on the periphery, then the 2 carbons need to bond with each other. Okay, so we're going to make a bond there. This carbon has 4 electrons around it as well. We have 6 hydrogens. Notice we have 6 unpaired electrons right now, so we're just going to put a hydrogen on each one of these. This is the structure of ethane. Okay, 2 carbons, 6 hydrogens, all single bonds. Alright, so let's try another one, C2H6O. So notice that these two are the same, except now we've added an oxygen. Alright, so let's figure out the valence. So we're going to have the same, right? So we have valence electrons. We have our 2 carbons is for 8. We have 6 hydrogens is 6, and we have an oxygen. How many is that? Is 6 more. All right, so we have 20 valence electrons. Okay, so let's start out again. Well, we can do this in several ways. Let's start out with having a carbon. All right, and we're going to bond this to either carbon or an oxygen. We'll find out we've got more than one possibility here. So let's attach it to the other carbon to start out with. We do it like this, and now we're going to add the oxygen. All right, and the oxygen is going to be on the has to go to one of these carbons. So let's just add our oxygen here. So there's 1, 2, 3, 4, 5, 6. All right, for oxygen. And now we can add our hydrogens. Notice, just like the previous one, we still have 1, 2, 3, 4, 5, 6 available lone electrons to make our bonds. Okay, so we can add a hydrogen to each of these. Alright, so this is the structure of ethanol. We saw that last time. Alright, so is this the only way that we could combine these atoms, though? Alright, still with the hydrogens on the periphery. Alright, there's another way that we could do this as well, right? So instead of bonding the 2 carbons together, what if we put the oxygen in between? Alright, so if we start with our carbon like this, we could connect that to an oxygen. Okay, that was our 1 for oxygen. Here's 2, 3, 4. We have 2 more. I'm just going to put 1 on the top and on the bottom. I could put it in any of those places though. And now I'm going to connect the other carbon to the oxygen. So there's 1, 2, 3, 4. All right. So now look, we have 6 available positions for hydrogens. This, like that. All right, so now we have 2 different Lewis structures that are equally fine. All right, so we could just call this, I'll call this dimethyl ether. Okay, when we have a carbon-oxygen-carbon situation, we have an ether. This over here is an alcohol, where we have the OH. All right, so we have 2 structures. These have the same molecular formula, okay, but they have a different connectivity of atoms. The one on the left has carbon-carbon-oxygen. The one on the right has carbon-oxygen-carbon. All right, but it has a different and these are called constitutional isomers. Okay, so isomers in general are just molecules that has the same molecular formula, but they're different from one another. If they're different in their connectivity like this, they're called constitutional isomers. We'll see a number of different types of isomers as we go forward. All right, so I'm going to make a new slide here, and we're going to look at these 2 other examples. All right, so the next one was CH2O. All right, so let's count up the valence electrons. We have our carbon, we have 4. We have 2 hydrogens, gives us 2, and we have an oxygen, gives us 6. All right, so this gives us 12 electrons. All right, so remember that in each final Lewis structure, you need to be showing this total number of valence electrons. Okay, so let's start out with our carbon, just like we did before. 4 electrons. Attach an oxygen. I'll put this one over here. Okay. And we have 2 hydrogens that we have to attach. Okay. So there's a number of ways that we could put these 2 hydrogens, right? We have 5 open electrons. And more or less by trial and error, we can come up with the right structure. Oftentimes, if we were doing this on an exam, it's not clear where we would put the atoms, the order of the atoms. I'll give you some kind of hint. All right. So what we're going to do in this case, we're going to put the hydrogens on the carbon. Okay. So I'm going to put hydrogen here, and I'm going to put another hydrogen over here. Okay. Okay, so we should have all of our atoms here now, but let's just count them up. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, looks like I forgot one. Okay, so we got to add one more hydrogen in here. Okay, electron, I mean. Okay, so I'm just going to put, it doesn't matter really where I put it, I'm going to put it over here. Okay, so notice right now the carbon has a complete octet of electrons. The hydrogens have full shells of electrons, but the oxygen doesn't. All right. So when we're counting for electrons in Lewis structures, for an atom to count that electron, it can count it if it's a non-bonding electron, or it can count it if it's shared. All right. So how many electrons does the oxygen have? All right, so it has 2 here. It can count 2, 4, 5, 6. All right, so it only has 6 here. And so what we need to do, if we look back at our rules, it says that we can complete our octet either with lone pairs or with multiple bonds. All right, so we're going to combine these two into a pair, and we're going to take this pair and we're going to put it in here to make a multiple bond. So we're going to make a double bond. So I'm going to redraw this like this, and now we're going to have 2 pairs in here, an oxygen here. There's that pair. Here's the other pair, and we have our 2 hydrogens. Okay, so now the way we can count this up is that if we look at the carbon, it can include all of the bonding pairs. So all of these can be counted. So this has 8. And for the oxygen, it can also count all of these. So it also has 8. All right, so we would call this a double bond because it has 2 pairs of electrons. Okay, we could also redraw this with just lines for electrons, for electron pairs and bonds. So it would be like this. All right. So notice this has this carbon-oxygen double bond. Remember, we called that a carbonyl last time when we were talking about polarity. Anybody know what this compound is? The simple compound. Probably smelled it in the biology lab before if you ever did dissections. This molecule is called formaldehyde. It has a double bond in it. All right, so let's do one more that was on the last slide. C2H2. Okay, so number of valence electrons. All right, so it has 2 carbons, right? 4 for each, gives us 8. It only has 2 hydrogens though, gives us 2. So we have 10 electrons. All right, we're going to bond the 2 carbons to each other. All right, we're going to add our hydrogens. Now, on the last time, we put both hydrogens on one end. We could try that, but I think through trial and error, we're going to find it's going to be better to make this symmetrical. Okay. Hydrogens are good. Carbons, though, need more electrons, right? Each of those carbons has 2, 4, 5, 6. They each need 2 more. So we're going to make some more multiple bonds. So we're going to take this electron and this one. We're going to move those together to make a pair there. And we're going to take these 2 and we're going to make another pair. Alright, so we're going to end up with 3 pairs of electrons between the 2 carbons. So that's called a triple bond. And we still have our 2 hydrogens on the end. Alright, so we could also draw this with 3 lines for the bonds. Okay, so this is more what we're going to be aiming for later, but when we do Lewis structures on exams and things like that, we're going to be showing all of our electrons as pairs, or as dots, right? So this molecule is called ethine. All right, and it's oftentimes also has a common name called acetylene. So it's a gas. Acetylene is a common gas used for welding. All right, so let's look add a couple more here, and we're going to bring in another aspect. So notice that each of these also has a charge now. Okay? So H3O, what's this called? Okay, you saw that back when you talked about acid-base chemistry, right? This is hydronium ion. All right, and if we do our valence electrons, we have an oxygen, 6. We have 3 hydrogens, which is 3. And we have this plus charge. What do we do if there's a plus? Right? Plus means that we have one less electron than we do protons, right? So we're going to, our plus, we're going to subtract an electron here. So 6, 9, so we have a total of 8 electrons to work with. Okay? So we're going to have our oxygen. All right, we can draw 6 electrons around the oxygen. We have 2 of our hydrogens, like this, and we have 1 more hydrogen, and so we're just going to put this hydrogen right here. Okay, because I already have 8 electrons. We don't have any more electrons to add, so we're just going to add that H. Okay, so oxygen, full octet. Each of the H's have a full shell, but we have this plus charge that we need to add. So what we're going to do is we're going to calculate what's called the formal charge in order to know where that charge goes. Okay, so here's the formula for calculating formal charge. So basically what this does is it compares the number of valence electrons that the atom has when we do our count up here. So oxygen has 6 to start out with, and we're going to compare that number to how many it has in the actual molecule. And when we do this type of bookkeeping now, it's going to be different than when we're just looking at complete octets. In this case, the atom can include all of the electrons if they're non-bonding, so those are unshared, but it only gets to include for itself half of the bonding electrons. Okay, so here's how this works. So we're going to calculate the formal charge for oxygen. Okay, so the formal charge is going to equal the number of valence that it started with. Okay, that's this number up here, 6. We're going to subtract from that the total number of the non-bonding and bonding electrons, and half the bonding electrons. So we're going to add the number of non-bonding electrons, so that only has 2 right here, 2 non-bonding. We're going to add to that half of the bonding electrons. All right, so we have 2 here, 2, 4, 6. So we have 6. Divide that by 2. All right. So we have 6 halves is 3. So we have 5 on this side. 6 minus 5 equals 1. So oxygen gets a plus 1 charge. All right, so that oxygen, because it donated a pair to make a bond to a H+, it gave away an electron, so it's short of 1. Okay. All right, so let's do hydroxide. That's this one, right? Okay, so the valence electrons, we have oxygen has 6. We only have 1 hydrogen is 1. What about the minus charge? Okay, the minus charge means there's 1 more electron than protons. So for the minus, we're going to add an electron. So this also has 8. All right, so we're going to have H bonded to oxygen. So there's 1 from oxygen. 2, 3, 4, 5, 6. We got 1 more to add. So we're just going to add that right there. So now oxygen still has a complete octet of electrons. All right, so let's calculate This time the formal charge for this oxygen, so formal charge is going to equal the valence for oxygen is 6. We're going to subtract from that the total number of electrons around it. It's going to have 6 non-bonding electrons, plus it has 2 bonding electrons, but we're going to divide that by 2. So we have 6 minus 7 equals a minus 1. Okay, so the oxygen in this case has a minus charge. Okay? All right, let's do one more example here. All right, so look at this one, CHO3 minus. Okay, let's leave us some room here. So let's do our valence electrons up here. Okay, we have a carbon, 4. We have a hydrogen, 1. We have 3 oxygens. How many is oxygen? Okay, oxygen has 6, so 3 times 6, 18. And we have a minus charge. And what does that do? That adds 1 more. Okay, so we add up to 24 valence electrons. Okay, so let's see if we can do this. All right, so what we're going to do, we're going to put the carbon in the middle. Carbon. All right, the 3 oxygens are going to go onto the carbon. Oxygen-oxygen bonds are pretty unusual. We see them sometimes, but they're pretty unusual. So usually, if we have something like this, all of those are going to go onto carbon. So we have 1, 2, 3, 4, 5. Let's see, 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. We have another oxygen over here. 1, 2, 3, 4, 5, 6. Got an oxygen here. 1, 2, 3, 4, 5, 6. All right, so we've connected all of our oxygens. So now we're going to add a hydrogen. All right, and it turns out we're going to add a hydrogen on one of the oxygens. Okay, so one of the oxygens has a hydrogen. That hydrogen is all happy, complete octet. All right, now what else do we got here? What do we got to concern ourselves with? All right, so carbon has a lone electron, only has 7. This oxygen has 7. This one has 7 as well. Okay, so do we have enough electrons here yet? Let's count those up. Okay, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Did I count those right? I don't think I did, but I think what we need is 1 more electron. 1 more like that. Okay, so now that oxygen has a complete octet, but only this one and this one don't. All right, so what do we do to complete their octets? Okay, we're going to take these two to go together and make a double bond. Okay, so we're going to have carbon, oxygen, here's its hydrogen. This one now is going to have 2 pairs and a double bond with 2 pairs on it. This one over here has like this. Alright, so we know we have a minus charge on here, so we got to figure out where the minus charge goes. Alright, so we got to calculate some formal charges here. Alright, so let's start with this oxygen over here. Okay, so this one has a formal charge equals the valence, right, is 6, just like we did before. We're going to subtract from that all the non-bonding, so it has 4. We're going to add to that half of the bonding, right, so it has 4 bonding electrons right here. So we're going to add in half of that, so 4 halves. Alright, so this is going to equal 6 minus 4 plus 2 is 6 is 0. Alright, so this oxygen is neutral. That one doesn't hold the minus charge. Alright, let's try this bottom one here. Formal charge equals 6, right? That's the same for all of the oxygens. So we subtract from that all the non-bonding, 4 non-bonding plus half the bonding. We have 2 bonding pairs, 4 halves. So we got 6 minus 6 equals 0. That one's not, doesn't have a charge on it either. Alright, so we have to fit in one more calculation. Let's go way up here. We can fit this in. Okay, let's do this oxygen. Okay, so the formal charge equals 6 minus, here it has non-bonding electron 2, 4, 6 non-bonding, plus the total number of bonding is only 2 halves. So on the right, we have 6 plus 1 is 7, so we get 6 minus 7 equals minus 1. Alright, so the minus charge is going to go on this oxygen over here. Alright, so this, in fact, this is the structure right there of, it's called a bicarbonate. Maybe I can redraw it up here. We've got a carbon, we have a 1 bond there, we have a double bond, and an OH with a minus over here. Let's call that bicarbonate, right? If we put a sodium there, sodium bicarbonate is the baking soda. Alright, so there's some examples of structures. We'll get some more practice on the problem sets and things like that. Okay, so let's look at some various trends. So we're going to draw out what we would expect for normal bonding for these atoms that we're going to use. Alright? And for each of these cases, we could go and we could figure out all the formal charges and stuff, but it's better if just by practicing this, we get to recognize these various situations. Okay, so for carbon, we know carbon has a valence of 4. Alright, so what that means is that when it's neutral, it's going to have 4 bonds. Okay? 4 bonds when neutral. Okay? Because it essentially has these 4 unpaired electrons. So we can see this in various ways. So we can either have a carbon that has 4 single bonds. Okay? We saw that in methane. We saw it in ethanol, dimethyl ether. These were all examples of carbon having 4 single bonds. Alright, we can also have a carbon that has a double bond and 2 single bonds. We saw this in formaldehyde. Or we can have a carbon that has a triple bond and 2 single bonds. Alright, each of these are situations where the carbon will be neutral. We saw that one for acetylene. Okay, so these ones are neutral. There are some other situations that are more the reactive intermediates and things like this. One possibility is that we have 3 bonds with a non-bonding pair of electrons. All right, if we have a lone pair like this, not a non-bonding pair, we got a lone electron. This is called a radical. All right. Or we could have a carbon that has 3 bonds, no other electrons, or we could have a carbon, 3 bonds, and a pair of electrons. All right, so these are kind of the 3 possibilities if we don't have a 4th bond. Okay, we could go through and calculate out the formal charge of each one of these. All right, so if we did that, the radical would end up being neutral. Okay, carbon with 3 bonds. Okay, we can do one of these. Okay, let's do this one. Formal charge equals valence of carbon is 4 minus the non-bonding. There's 0 non-bonding plus half of the bonding. Okay, 4 minus 3. This has a plus charge on it. All right, if it's plus there, we add 1 electron to here, would go to neutral. All right, we add 1 more electron to go over to here. What should it be? This is going to be a minus charge. Okay, so this is it's called a carbocation. We're going to learn a lot about those in a few chapters. And this one would be called a carbanion. Okay, so these are all the different possible forms of carbon. All right, for nitrogen, how does the number of valence electrons differ for nitrogen? Okay, nitrogen is to the right of carbon, so it has 1 more valence electron. So it's going to have 5 valence electrons. Okay, if we draw it out like that, how many bonds do you think it's going to make when it's neutral? Okay, it has 3 lone electrons, so it's going to make 3 bonds when neutral. Okay, so like carbon, nitrogen can have 3 bonds and a non-bonding pair of electrons, and it would be neutral. All right, it can have a double bond and a single bond, or you can have its non-bonding pair and a triple bond to something else. In each of these cases, these are kind of bonds to some other atom. All right, so all of these would be neutral. Okay, we could have reactive species over here. We can have nitrogen if it has 4 single bonds to it. This ends up having a plus charge. All right, this is called an ammonium ion. All right. All right, so oxygen, let's go to the next one. Oxygen has 6 valence electrons. Okay, so if we draw it out like that, how many bonds should it have when it's neutral? Okay, it has 2 lone electrons, so it has 2 bonds when neutral. Okay, so oxygen can either have its non-bonding pairs with 2 single bonds, okay, like in water, right? Or you can have its 2 non-bonding electrons with a double bond. All right, so we saw that in formaldehyde, we saw it in bicarbonate. All right, there's also some reactive forms of oxygen. We've already really seen these. Oxygen can have 3 bonds and a non-bonding pair. This is like in hydronium ion. This has a plus charge, or it can have an oxygen connected to something with 3 non-bonding pairs, and so this one would be a minus charge. That's like in hydroxide. All right, the last group of atoms that we want to be able to recognize quickly and work with are hydrogen and the halogens. Okay, so let's do the halogens. The common generic form of halogens is X. Generic halogen. Okay, so fluorine, chlorine, bromine, iodine. Those are the ones that we're going to be concerned with. All right, so it's the valence here for halogens. The valence equals 7, right? So how many bonds is a halogen going to make when it's neutral? Right, so it's going to make one bond, right? X with a single bond. All right, that's going to be neutral for a halogen. What about hydrogen? Hydrogen has a valence equal to 1, like this. So hydrogen, likewise, is only going to make a single bond when it's neutral. All right, but there are, again, 3 forms of hydrogen. Okay, so we can either have hydrogen like this, we can have hydrogen with no electrons, or we can have hydrogen with a pair of electrons. Okay, so hydrogen with an electron, this is just the hydrogen atom. Right, so it's neutral, 1 electron, 1 proton. If we have hydrogen with no electrons, then it gets a plus, right? And because all that's left is a proton, we call it a proton. Right? So we see that a lot in acid-base chemistry, right? It's a proton, because that's all it is. And if we have a hydrogen with 2 electrons, has 1 more electron than it has protons, this is H minus. This is called a hydride. Okay? Halogen as well, right? Its most common one is, like we already saw before, is X minus. All right? So these are all common situations. So as we go through the class, we'd like to be able to know, if we look at a structure and we say, oh, that oxygen, look, it's got 3 bonds to it here. It needs to have a plus charge. It has a plus, right? Or we could have that same oxygen with a double bond like this, and a single bond and a non-bonding pair, right? But again, it has 3 bonds and a non-bonding pair. We know that, oh, that situation, it has a plus. Okay? So we'd like to be able to recognize that and not have to stop and do our formal charge calculation every time, right? So same for nitrogen, same for carbon. You know, we can memorize these now, but a lot of them we'll be able to just get used to. All right, so Lewis structures, though, are pretty cumbersome and slow. All right, and so what we'd like to do is get to some structural drawings that we can do in a much faster, more efficient manner. Okay, so we're going to look at 2 different ways, and these still aren't that great, but they're going to be better than drawing out full Lewis structures. Okay, so the first kind I'm going to look at are called the condensed structures. And these are really what we would write out if we just wanted to write them out on a keyboard, right? Everything in a line. Okay, so for condensed, right, we could have CH4. Okay, this is a condensed structure. This is of methane. Okay, for the Kekule, that's how that's pronounced, we're going to draw out all the bonds as lines. So we have lines for bonds, and we don't draw in any of the non-bonding electrons. Okay, sometimes we can kind of have hybrids of these, all right? But if we have methane, we just have a carbon with 4 bonds to hydrogen. All right, so this is a Kekule structure. All right, so let's do another one. Okay, so CH3, CH3. All right, so this is ethane. Okay, it's condensed structure. Each time when we see three H's here, they always go on the carbon that's written before it. So these three go there, these three go over here. Okay? If we want to draw the Kekule structure, we have our two carbons attached to each other, H's all around. So this really shows us all the bonds. Alright? Alright, so let's do a couple more here. What if we had a longer chain? We could do something like this. You might see if we have some CH2s, we want to put them together here. CH3. Okay, so then we have a CH3, 4 CH2s, and then a CH3. Okay, there's a molecule called, so this is ethane. It's called hexane. We'll learn about the naming later, but as you can already kind of notice, is if we have this ANE, all these have the same, it's all carbon and hydrogen single bonds. All right? So if we're going to draw out the Kekule structure here, right, we're going to have 6 carbons, 1, 2, 3, 4, 5, 6. We're going to have to draw in all of the hydrogens, and oh my god, I'm already getting tired of doing this. It takes so long, and it's so slow and so cumbersome, and if we had to do this every time, it would take like 3 years to be able to do organic chemistry. Alright, so I'm going to show you in a second a faster way to do that. Alright, so let's do another one here though. CH3, CH, OH, CH3. Okay, sometimes this OH, you might see it in parentheses here. It's just separated. But again, whatever's after the carbon, so this H goes onto that carbon, this OH also goes onto that carbon. Okay? So this molecule is called isopropanol. Anybody know what that's for? Or what it's called commonly? All right, this is called rubbing alcohol. I don't know who rubs it on all the time, but that's what it's called. All right, so if the Kekule structure, all right, so these H's, and then we have another CH3 over here. All right, and then on this middle one we have both an H and an OH. All right, so let me just make a point here. This is one structure of isopropanol, but I just chose to draw these 3 carbons in a line like that. I could also draw this like this. Here, I'm going to draw a line there. Let's draw a line in there. See, like that. And what do you think? Is this the same thing, or is it something different? Is it an isomer? Okay, these two are exactly the same. So it's not important whether these are in a line or whether they're in a curve or a corner here. What's important is that the 3 carbons are connected to each other, right? And that the OH, the alcohol, is connected to the middle one. All right? Okay, so a couple of other things that I'll show you here is that we usually always, on this OH, all right, I'll do this in blue down here, a couple of things to avoid, if we draw the OH on this side over here, what we want to do is draw the bond to the oxygen. And so we'll put the H on the other side. All right? So this is better. So if we did it like the other way around, like that, that looks like the H is between the carbon and the oxygen, and that just looks dumb. So we don't do it that way. Okay? It's not what cool organic chemists do. So we always try to make that bond between the carbon and the oxygen, and then the hydrogen goes on the outside. Okay? Sometimes we'll do that with things like those CH3s as well, though it's not always consistent like this. Okay, sometimes you'll see it like this, CH3, right? So that's probably even better than having it like this. Okay, because this one shows that this bond is between oxygen and carbon. This one has the H's in between, so I would say that this one is a little cooler than this one over here. Alright, though you'll see it's like this sometimes too. Alright, just some be cool organic chemists. Alright, so the better, most straightforward types of structures are what we call the skeletal structures. Okay? And skeletal structures are much simpler to do once you know what they are, right? And in this case, we're going to omit both the carbon and the hydrogen. So how can we draw a structure if we don't draw any carbons or hydrogens? Well, we're going to draw structures that just have lines, and we're going to assume that there are carbons on the ends of the lines and at the junctions between the lines. All right? And we're not going to draw on the hydrogens on carbon. We're going to draw it on other atoms like oxygen or nitrogen. But we're just going to assume that there are enough hydrogens to give carbon a complete valence. All right? So let's draw out, here I'm going to draw out a big Kekule structure. Okay, and if we want to draw a bigger one like this, it's going to take us forever. Okay, we could have another CH3 up here, and another CH3 over here. And let's just put an H here. Alright, so see how long that took me. Alright, so when we do skeletal structures, what we're going to do if we have just a carbon chain is that we're going to draw it as kind of a zigzagging line. Alright, and I'll tell you later why we do that, or I'll show you later why we do that. It has to do with the stability of the chain. Alright? So what we want to notice here is how many carbons we have in a row. Right? So I could count these 1, 2, 3, 4, and either I could go to the right or the top, it doesn't matter. I'll just count 5. Alright, so we have 5 carbons in a row. So I'm going to start here and I'm going to go 1, 2, 3, 4, 5. Okay? So when we draw this, wherever there's a junction, like right here, there's a carbon, here, 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 or at the ends of the lines, there's carbons. Okay? So these are all carbons. Alright? So there's our 5. And then what we could notice is we count from 1, 2. On the second carbon, we have an OH. Okay, so I'm going to count 1, 2, and I'm going to draw the OH right here. And then I'm going to go 3 and 4, and 4 has another CH3 group, has another carbon, and so I'm just going to add another carbon. Okay? So this is a skeletal structure, which is the same as the one up above. Alright? So we can also draw this in various ways. So I ended up just starting low, going up up, down like that, but I could also reverse those. Alright, so I could put the OH here, like that. Alright, what do you think? Are those the same or are those different? Okay, these two are the same. In fact, all we would do is if we took one molecule of here, if we just kind of flipped it over, we could lay it right on top of that. So it's just been kind of rotated in three-dimensional space. Okay, so those are the same. Okay, what if I drew a structure like this? What do you think? Is that the same as the other two, or is that one different? Okay, that one is the same as well. Alright, and what we need to recognize, so in this first one, so if we counted it like we did the top one, 1, 2, notice we have an OH on the 2 position, 3, 4, 5. Here we got the same thing, 1, 2, OH, 3, 4, there's a carbon attached, 5. So how would we number this one on the right to make that fit the pattern here? Okay, so on this one, if we start numbering over here, we got 1, 2, then we have the OH there, 3, 4, 5. Again, we have a carbon at the 4 position. All right, so we can draw it in different ways. The 2 on the left and in the middle, we kind of have this this zigzagging up and down here. I just drew it a little different here, but that's still the same. So let's look at one more. What about this one? What about that? Is that the same? No, that one's different. Okay, because again, if I start numbering over here to the left, 1, 2, 3, 4, 5, notice that this OH is now at 3 rather than 2. Alright, so what's the difference here? What would we call these? So these are all the same, and this one is different, and these are called constitutional isomers. So just like we saw before, these bottom three, well, they're all the same. Compared to the one on the upper right, we have the same molecular formula, but the connectivity is different. All right, so they're constitutional. All right, so that's our practice in drawing. So look in the book. There's some tables in the book that show lots of different structures, examples of these Kekule structures, skeletal structures. You'll want to be able to convert one to the other and back again, right? And we'll want to make sure that we know when we look at those Kekule structures that we know what they represent. We know how many hydrogens are on each of the carbons. We can look at a structure and be able to count up the formula from the drawing and back and forth. All right? On the next video, what we're going to do is we're going to start to look at the three-dimensional shape of organic molecules and how we can use the orbitals to make those molecules up.